In this video, I'm going to look at the graphs of inverse hyperbolic functions. Let's start with y equals sin x. Here we've got the graph of y equals sin x. The domain is x can be any real number. And if we want the inverse graph, we just reflect in y equals x. And there we have the function y equals r sin x, which also has domain x can be any real number. So x is any real number, and for r sin x, x is also any real number. What happens when we look at y equals cos x? If we take y equals cos x, if we start by looking at the curve of y equals cos x and reflect in y equals x, we get this curve. The blue curve is no longer a function. For one value of x, we get more than one, we get two values of y. So we have to restrict the domain of y equals cos x. It makes sense to restrict that to x greater than or equal to 0. Then the reflection in y equals x is just the top part of the blue curve. So if we do that, we have this picture. Now, when we're looking at the graph of y equals cos x, we have to restrict x to be greater than or equal to 0. And for y equals r cos x, x has to be greater than or equal to 1. That is in order to make sure that we have a function when we're looking at the inverse. Just looking at the others, when we have y equals tan x, that lies between -1 and 1 and is defined for all real values of x. The inverse function, y equals r tan x, or r tan x I should really say, is only defined for x between -1 and 1, mod x less than 1. Y equals cos x is 1 over tan x, 1 over tan x. That is defined everywhere except x equals 0. And as you come down with cos x, it comes down to but never reaches 1. It's always bigger than 1, and it's always smaller than -1. So when we reflect that graph in y equals x, the blue graph will always be outside -1 to 1. Y equals r cos x, mod x must be greater than 1. And then, when we come down to look at r sec x, this has the same sort of problem as we had when we had cos x. If I take the whole graph for sec x, when I reflect that in y equals x, I will get a graph which gives me two values of y for one value of x. So then I would not have a function. In order to make r sec x a function, I must restrict things, and once again it seems sensible to take positive or 0 values of x for sec x. When I then reflect that part of the curve in y equals x, I get this bit here. And so y equals sec x in this case is only defined for x greater than or equal to 0, and y equals r sec x, 0 must be less than x, less than or equal to 1. And for cosec x, that's 1 over sin. 1 over sin is going to have a problem at the origin. So cosec x is not defined for x equals 0. So we look at the red curve and reflect that in y equals x. We get the blue curve, which is the inverse r cosec x. And that again has a problem at the origin. So that is defined everywhere except x equals 0.